was a postdoc fellow from 2016 to 2017 at the Hebrew University of Jerusalem, and she was a research fellow at the Simon Institute for the Theory of Computing at UC Berkeley in 2015. She received her PhD at Aarhus University in Denmark in 2015. Her research was supported in part by an IBM PhD fellowship and a Google Anita Brock Memorial Scholarship. During that time, she also visited CMU and the IIIS at Tsinghua University. Professor Brownze's research interest lies in theoretical computer science and artificial intelligence, in particular, algorithmic game theory and theoretical aspect of learning. Let's welcome Professor Brownze for her wonderful talk.
Well, thank you for the introduction and for inviting me. So I'll talk today about multiplayer bandit learning from competition to cooperation. This is based on joint work with Yuval Perez. So in this model, there will be, so feel free to interrupt me with any questions throughout the talk. So in this model, there will be two players, Alice and Bob, that play in a multi-arm bandit problem. And one arm is safe, which means that it has a known probability of success P. So basically, when you pull the arm, you either get a success or failure, which we will model with a 1 or a 0. So it's a Bernoulli bandit. So one arm is safe, and the other arm is volatile, which means it has an unknown probability of success theta with a prior mu, and the prior mu is known. And the following game will be played between the players. In every round, each player pulls an arm, gets the reward, which could be 0 or 1 from the arm they pulled, and then observes the action taken by the other player, but not their reward. So this is a pictorial representation. So we can see Alice and Bob. So we have the left and the right arm. And in green, I showed the action taken by Alice. So for example, in round 1, Alice pulls the left arm and Bob pulls the right arm. To fully specify the game, we have to say what the utilities are. So Alice's utility will have the form gamma A plus lambda times gamma B, and similarly for Bob, where gamma A will be the discounted reward. So it will be the sum from time going from 0 to infinity of little gamma A of t times beta to the power t, where beta is the discount factor and little gamma A of t is the utility that Alice got in round t. So her reward for round t, so basically 0 or 1. And there will be a definition for finite horizon, which is similar. So there gamma A is the sum from t equals 0 to capital T of little gamma A of t. So here it will be simply the sum of rewards. And so the results will actually also be for finite horizon. There are some similar phenomena, but I will focus on the setting with the discounted gain due to time constraints. So there are 3 settings that we will focus on. So one is a competitive setting, which is a zero-sum game, and this can be modeled by taking lambda equal -1. So here Alice's utility is gamma A minus gamma B, and Bob's utility is gamma B minus gamma A. So here, basically, each player wants to get more rewards than the other one, and they care about the difference. And one example you could imagine is competing from companies in a saturated market. So basically, each customer that is gained by one company is lost by another one. The case where lambda equals 0 means that Alice's utility is gamma A and Bob's utility is gamma B. So basically, they only care about their own rewards. So we could think of this as they're completely selfish. And then there is the cooperative setting where lambda equal 1, where both Alice and Bob have utility gamma A plus gamma B. So here the players are aligned. They optimize the same function and they try to maximize the total rewards collected. And there is evidence that source of food, then that is good for the whole nest. She will still do it. They're programmed this way. And there are other settings for other values of lambda. So for example, lambda equal a half could model players that are partly aligned, like then Alice would have utility gamma A plus half times gamma B. So she wants to maximize her rewards plus, but she also wants her sibling to be happy. So this could in principle model siblings like which share half of the genes. So the strategy will be a map from history to the next action to play and maybe randomized. So basically Alice's history will mean that Alice can see actions taken by both players in each round, plus Alice's rewards, which she can see all of them. And the same for Bob. So the only thing that Alice doesn't know, she doesn't know the rewards that Bob received. And the expected utility will be computed using the player's beliefs about the private information of the other player. A relevant quantity in the bandit setting is the Gittins index. So this will be denoted by G, and it will be a function of the prior mu and the discount factor beta. So we'll say that the Gittins index of the risky arm is defined as the infimum of the success probabilities P, where playing always a safe arm with probability P is optimal for a single player. So basically, like in the picture here, if we have two arms, one has a probability of success P, it's safe. If we play that arm every time we get a reward with probability P, the other arm we know less about, but we know it has a prior mu. So its probability of success is drawn from the prior mu. Then, so the Gittins index basically says when the player is indifferent between these two arms. When the player could stop experimenting with the risky arm and retire in some sense, so then play the safe arm from that point on. So it could be seen as a retirement value. So what payment P would the player accept to stop exploring? And I should also note that the Gittins index G is greater than M, where M is the mean of mu. And this is for the case, by the way, where mu is not a point mass. The optimal strategy of one player that faces K risky arms is that in each round, the player should pull the arm with the highest Gittins index at that point. So basically, if the player is alone playing in this game, then and faces K risky arms, and in every round, he computes the Gittins index of each arm and then pulls the arm with the highest index. I should mention some literature on multiplayer learning in Bandit. So there has been a lot of work in the so-called collision model, where the players are cooperating. Basically, they're pulling arms independently. So they try to maximize the sum of rewards, and they can agree on a protocol before play, which is part of their cooperation, but then they're unable to communicate during the game. And whenever there is a collision at some arm, then no player that selected that arm receives any reward. And this models some network settings, basically, where if two players pull the same arm, it's like they try to use the same channel, and then both of their messages get garbled. So this model has been studied in an adversarial setting, where basically the rewards for the arms are generated by an adversary, or the stochastic setting, and also whether the players receive input about the collision or not, like whether the players have any idea that they collided, or it just happened that they got a 0. There is also multiplayer bandit learning in the same feedback model as ours. So in particular, Ayagi studies 2 risky arms where the priors have discrete support. And Rosenberg et al. Studied the same model, but where the decision to switch to the safe arm is irreversible. So this is, again, two arms. One arm is safe, one is risky, and the players can play either one, but if they switch to the same arm, to the safe arm, then they cannot go back. And there has been also work in R&D literature on the interplay between competition and innovation. Okay, and there is also work on multiplayer bandit learning where the feedback model is such that the feedback is immediate. So the players, the only bit of uncertainty is what happens in the current round. So Alice and Bob know everything that happened in the history, and then they decide what to play in the current round, and then they see right away what the other player got. Are there any questions at this point?
Yeah, are there any questions from the audience at this point?
Yeah. You said there is a question, or there is no question?
No, I'm asking.
Oh, okay. Sorry, I thought you told me.
Okay. Doesn't seem so. Yeah. Could you just continue?
Okay. So, okay, and there is also work on incentivizing exploration. But that's a different model where there is a principal that wants to explore a set of arms, but the exploration is done by a stream of myopic agents, and they may choose to basically do something myopic and not do as much exploration. And this also has some connections with evolutionary biology, where the question is how cooperation evolved in insects like ants and bees. And there are studies by Hamilton Anderson and others basically showing that insects that are identical or almost identical genetically, they cooperate more than other animals. Okay, so in the competitive setting, so this is the first I'll focus on. This is a zero-sum game, and it can be shown to have a value. This is a direct consequence of the science minimax theorem. And the question is, how do competing players behave? So the first theorem will say that competing players explore less. So to quantify this, suppose the arm L, so this is the safe arm. So let's say the safe arm has known probability P, and arm, the risky arm has IID rewards with unknown success probability with a prior mu, which is not a point mass. And then Alice and Bob are playing optimally in the zero-sum game, which has a discount factor beta. And then the statement is that there exists a threshold P star less than G. Remember that G is the Gittins index of the risky arm, such that for all probabilities P greater than P star, with probability 1, the players will not explore the risky arm. So basically, the players, if there was a single player instead exploring these two arms, then that player would play, by explore, I mean that whether they will play the risky arm even once. So basically, if we have a safe arm with probability of success P and a risky arm with a prior mu, then there is a range between P star and G and the Gittins index of the risky arm, where neither of the two players will play even once the risky arm, even though a single player playing optimally would. And this can also be quantified a bit. So this P star will be less than M beta plus G over 1 plus beta, where M is the mean of mu. So I want to give some intuition for what happens here. So suppose that Alice and Bob started the safe arm, and then Bob wants to explore the risky arm. And he goes and explores the risky arm, he plays it once, and let's say he finds some gold in there, it looks better. He plays it a few times, he gets very good rewards. Then Alice can see that Bob is playing the risky arm. So from that, she can infer that the rewards there are better. And she can join him at that arm. And that basically will reduce Bob's advantage. So it's like he can only take advantage of this for some small number or finite number of rounds until Alice will figure out what's going on. However, Bob took a risk. It might be that the risky arm is actually very bad, and Bob is incurring this risk. He's going to explore the risky arm, and maybe it doesn't go so well. He's incurring losses there. So basically, overall, his expected utility, or I should say advantage compared to Alice from this, doesn't justify doing it all the way up to the Gittins index of the risky arm. So he will be a bit more conservative and may not explore it even if the probability is above some P star, which is less than the Gittins index. So, okay, this is a pictorial representation. So we have 0 and 1. So the values are between 0 and 1. M is, let's say, the mean of mu, and then we have the Gittins index shown with G, with the risky arm, and then P star. Basically, one player will always explore in the range from 0 to G, the risky arm. So here the risk arm is shown on the right. But competing players will not explore in the red region from P star to G. And in fact, they won't explore anywhere above P star. So we can see from P star to 1. So theorem 1 shows information is less valuable in the zero-sum setting. And then there is a question whether does it have any value? Like, do the players behave completely myopically by going and pulling in each arm the arm with the highest mean? And this is in fact not the case. So competing players are not completely myopic. And so in the same setting as before, there exists a threshold P tilde greater than M, where M is the mean of the risky arm, such that for all P less than P tilde, with probability 1, the players will explore arm R in the initial round of optimal play. And this can also be quantified. So P tilde is more than M plus beta W over 2, where M is the mean of mu and W the variance. Okay, so this is a more complete picture, which also has the green region, where from 0 to P tilde, the 2 players will explore. So they will play the risky arm at least once. From P star to 1, they won't. And we think that P tilde and P star are equal, but we're not able to show this. So that's why there's a dotted line connecting them. Okay, so for the cooperative setting, so here the players maximize the sum of the rewards and they can agree on the strategies before play. So what we find is that cooperating players explore more. So basically, so in the same settings, we have Alice involved, we have the safe arm with probability P, the risky arm with prior mu, the discount factor is beta. Then there exists P tilde greater than G. This should be P hat greater than G. So that for all P less than P hat, at least one of the players explore the risky arm with positive probability under any optimal strategy pair that maximizes their sum of rewards. So basically, if competing players are more conservative, then cooperating players are going to explore even above the Gittins index. And the intuition is that if they find something good there, then this is good for the whole team. So they are more going to be more risk-taking. And this shows again also the region. So the picture also illustrates P hat, and then in the region from 0 to P hat, the cooperating players explore. But still they won't. So we also show they actually don't explore above some P0, which is from P0 to 1. And again, there is a question if these two thresholds are equal. And then in the neutral setting, the utility of each player is their own reward. And the solution concepts that are relevant will be Nash equilibrium and perfect Bayesian equilibrium. So here to briefly define that player I strategy sigma is the best response to player J strategy sigma J, if no strategy sigma I prime achieves a higher expected utility against sigma J. And a mixed strategy profile sigma I sigma J is a Bayesian Nash equilibrium if sigma I is the best response for each player I. A perfect Bayesian equilibrium is the version of subgame perfect equilibrium for games with incomplete information. So basically, a bit more formally, a pair of strategies sigma I, sigma J is a perfect Bayesian equilibrium if starting from any information set, subsequent play is optimal, and moreover, beliefs are updated consistently with Bayes' rule on every trajectory that occurs with positive probability. And such equilibria are guaranteed to exist in this setting. And the difference basically from Nash equilibria is that in the perfect Bayesian equilibrium, there cannot be non-credible threats. Like Alice cannot threaten Bob, if you do this, I'll retaliate in some terrible way. Because if that is not believable, then the threat doesn't really carry any weight. So the question is, does each neutral player play the one player optimal strategy, for example? Which would be to pull the arm with highest Gittins index in each round. So that turns out to not be the case. And the phenomenon that we find is that at the high level, neutral players learn from each other from a range of parameters. So again, we have the same setting with Alice and Bob. And there are two things that happen. So one is that in any Nash equilibrium, for all P less than the Gittins index, G, with probability 1, at least one player explores. And moreover, the probability that no player explores by time t decays exponentially in t. So here it's also possible to bound the time by which they explore. And now suppose that P is in the interval P star and to G, where P star is the threshold above which competing players do not explore. Then if the equilibrium is also perfect Bayesian, so is this more refined concept that is used in repeated games where we don't allow non-credible threats, then every neutral player has the expected reward that is strictly higher than a single player using an optimal strategy. So this means basically that the players can learn from each other in a very perfect Bayesian equilibrium. And this can happen, for example, by them taking turns in who does the exploration, and this will help them incur, like, overall the risk will be kind of distributed. Okay, so this is a more complete picture which has all the thresholds. So now there is the kind of bright red region from P star to G, and then from where neutral players learn from each other. Okay, are there any questions at this point?
Yes, I've seen there are many questions from the audience that we read them one by one. Yes, maybe.
Oh, sorry, let me see. I can see the chat.
Yeah. Okay.
Oh, what is the Gittins index? So, okay, I guess I explained this earlier. So the Gittins index is a value that you can define in any setting where you have multiple arms, and it's a threshold. It's like kind of like you can think of it as like an expected value for the arm, but it's not just the mean of the prior, but it's something that also takes into account how valuable that arm is if good things happen in the future or bad things happen in the future. So it's different from the mean. It's actually higher than the mean if the prior is not a point mass. And the motivation, so this comes from statistics, and it's basically very useful because it says what is the optimal strategy for one player playing K arms. The player should pull the arm with the highest Gittins index in each one. Does the model have real applications? Okay, maybe we can discuss this at the end. So it's is the neutral case equivalent to a case with two independent band learners? No, it's not. The agents know each other's utility function, but they don't know what rewards the other players got. And there is a question if it's possible to generalize to the case where the safe arm is also unknown. Right, so the safe arm then would no longer be safe. Yeah, I think that's very interesting to generalize to K arms, like how players behave if there are K arms. Okay. So there is a question. So here I talked about what happens if the players are exploring at some point versus not at all. But what happens in the long term with their strategies? And this is related to some work in economics by Rothschild and follow-up work by others. So Rothschild studied a single player two-arm bandit problem and showed that the player ends up with the wrong arm with positive probability. And he conjectured that this can actually also happen with two players that are observing each other's actions, that they may settle on different arms. And roughly the high-level reasoning, so this is taken from a discussion in a paper by Agi, is that if you have two players, so basically the single player might settle on the wrong arm, but even if there are two players, they may settle on different arms, both thinking that is the other player who's playing the wrong arm after they've had bad draws from one of the arms. And Ayagi actually proved convergence, proved that two players playing a bandit game this is for the neutral setting with two arms, that they settle on the same arm in the case where the priors are discrete. Now this turns out to matter. So in our setting, the priors are not necessarily discrete, and when the priors are discrete, you can do induction and eliminate possibilities. After you've had enough observations, you can rule out values of the probability that are in the priors. But with a continuous prior, you can no longer do that, so it would need a different approach. Okay, so and Rothschild has an example with stores and whether you could have two stores charging different prices for a product and each thinking that so the store in B is selling books and the fact that B is charging a different price is not conclusive evidence that A is doing the wrong thing, and they each have some data that the other one doesn't have, and that this way they might each kind of settle on their different price. Now on the other end of the spectrum, there is Aumann's agreement theorem, which says that rational players with common knowledge of each other's belief cannot agree to disagree. So the bandit setting has elements of this Aumann's agreement theorem. So the question is, do the players settle on the same arm in the long term? But it also has elements that are not found in the setting of Aumann, which is that players keep getting different information because they keep the kind of uncertainty keeps accumulating because they cannot see each other's rewards. So when lambda equal 1, there are Nash equilibria where aligned players do not settle on the same arm, where one player alternates infinitely often between the two arms. This is an example which I won't. I can go more into it offline. I won't have time to cover it, but basically there will be a setting where Bob can visit both arms infinitely often. So this is for Nash equilibrium. Sorry, I think I said, so this is for aligned players in the Nash equilibrium. So basically, it can be the case that one player is given a schedule, like to visit, like in this case, Bob, to visit the safe arm every 5 rounds or every 6 rounds. And then Alice will stay at the good arm, in this case, the arms are known. So the risky arm is better than the safe arm. And then Alice will play the good arm if Bob follows the trajectory, but if Bob ever deviates from it, then Alice will switch to playing the safe arm forever, which will be worse. So she kind of punishes him for deviating. However, what we show is that so competing and neutral players will settle on the same arm. So roughly we have the left arm has success probability P, the right arm has prior mu. That has no point mass. Then in any Nash equilibrium, in both the competing and neutral cases, the players eventually settle on the same arm with probability 1. So here the intuition is that basically the players, so if both players explore finally many times, then we're done. Otherwise, there is a player, let's say Alice, who explores infinitely many times. And then Alice will eventually know which arm is better. So if she continues exploring, then it must be that theta is greater than P, where theta is the probability of the risky arm. So then if Bob sees that Alice keeps exploring, he will eventually realize that theta is greater than P and will join her with the right arm. But the challenge in the continuous setting is that theta might be very close to P, so this will delay the time at which Alice can determine the better arm. Okay, so I will stop here. These are some questions for the discussion, but I don't want to go over time. So perhaps, if you have any question, you can ask me after I conclude the talk.
Okay, thank you, Professor Brente. Unfortunately, we are running out of time, so we do not have time for the questions. Maybe the last, or maybe could you answer the last one in the chat? After that, I think we have to stop here.
When lambda is positive, Alice and Bob may choose different arm. Is there a threshold of lambda from -1 lower than this result? Sorry, I didn't. So we have some results actually also for other values of lambda. So in this talk, I mainly talked about lambda when it's -1, 0, and 1. We actually do have some results in the paper also for a range of lambda. But I'm not sure I understand the question, sorry. Whether if lambda, if there is a threshold such that below the threshold, Alice and Bob choose the same arm. Yeah, I'm not sure actually, I don't know.
Okay. Yeah, sorry, unfortunately we have to stop here. Maybe you can talk, you can communicate offline later.
Okay.
Let's thank Professor Brandon again for giving us such a wonderful talk.
Oh, thank you for the invitation. So I'll stop sharing my screen and mute myself.